Have you ever wondered whether we can keep zooming into nature forever? Each new tool we've built has taken us deeper into that unseen world. Early microscopes revealed tiny cells and wriggling microorganisms, invisible to the naked eye. Electron microscopes took us deeper still, showing individual atoms. But can we go further? Well, the answer is yes. The Large Hadron Collider at CERN is the most powerful microscope ever built. It reveals the structure of matter at scales hundreds of millions of times smaller than an atom. Yet, as we'll discover in today's video, if you keep pushing, channeling more and more energy into ever smaller regions of space, something truly remarkable happens. The very act of trying to look closer makes spacetime itself collapse, creating a black hole. And this suggests an operational limit to our most successful theories, a sign that something new is needed, perhaps a framework like string theory, which posits tiny one-dimensional vibrating strings as the fundamental building blocks of nature. But to understand where these boundaries lie, let's start with a simpler question. How do we see the world around us in the first place? Well, in order to see something, we need to scatter light off it. This requires three ingredients: a light source, the object itself, and a detector like your eye. Then the light from the source can scatter off the object and into the detector. Roughly speaking, the smallest detail we can resolve depends on the wavelength of the light we use. There's a simple rule of thumb. We can only resolve a feature if the wavelength of the light is roughly the same size or smaller than that feature. It's a bit like a ship on the ocean. If the wavelength is much bigger than the ship, the water rises and falls almost uniformly across the hull, so the ship mostly rides up and down and the wave barely notices it. But when the waves are comparable to or shorter than the ship, they scatter and reflect strongly from the hull. Okay, so imagine we want to shine light onto an object and resolve a feature of size delta x. We therefore need light whose wavelength lambda is roughly less than or equal to delta x. So far, so good. But at the beginning of the 20th century, Albert Einstein made a profound discovery. He realised that a beam of light actually consists of a stream of tiny fundamental particles called photons, and this allowed him to explain the photoelectric effect. Einstein realised that each photon must have a well-defined momentum and energy which we can calculate if we know the wavelength, lambda, of the light, along with Planck's constant, which has a tiny value of 6.63 times 10 to the minus 34 joule seconds. This means that if we wish to resolve details of size delta x, we need photons with a wavelength at least comparable to this size, which implies a photon with energy roughly equal to hc divided by delta x. And this tells us something profound, that to see smaller things, we need light with higher energy. And this is because shorter wavelength light corresponds to higher energy photons. Now, because visible light has wavelengths around half a micrometer, visible light can be used to resolve things like hairs and cells, but not atoms. Even the best optical microscopes are diffraction limited to about 200 nanometers. And so the reason we cannot see individual atoms with sizes of around 0.1 nanometers is because visible light has a wavelength that is thousands of times larger than the size of an atom. And so if we wanted to resolve individual atoms, we would need wavelengths comparable to or smaller than the atoms themselves. That's why X-rays with wavelengths of around 0.1 nanometers can reveal individual molecules and even the atomic structure of crystals. Now, one of the great discoveries of the early 20th century was that not only light, but all matter behaves like waves. Louis de Broglie showed that every particle of matter, electrons, protons, even whole atoms and molecules, has an associated wavelength given by exactly the same relation as for photons. Lambda equals h divided by p, where p is the momentum and h is Planck's constant. And so matter itself can act as a kind of wave. This means that we can use particles like electrons as probes to see small structures, applying the same logic that we used for light. The shorter the de Broglie wavelength, the finer the details that we can resolve. So let's consider an example. Suppose we want to be able to resolve individual atoms of size 10 to the minus 10 meters. For an electron to have a de Broglie wavelength this small, we can work out what its momentum must be by rearranging the wavelength equation. If we then set the de Broglie wavelength equal to the size of the atom, and then plug in the numbers, we find a momentum value of around 6.63 times 10 to the minus 24 kilogram meters per second, which corresponds to an electron velocity of around 7.3 times 10 to the 6 meters per second, which is around 2.4% the speed of light. Okay, now let's actually calculate the kinetic energy that an electron would need to have this velocity and momentum. According to Einstein's theory of relativity, the total energy of the electron can be calculated using the relation E equals the square root of p squared c squared plus mc squared all squared, where m is the electron's rest mass and c is the speed of light. It then follows that the kinetic energy will be equal to the total energy minus the rest mass energy, which is the energy the particle has at rest just by virtue of its mass. If we then sum in the equation for the total energy, we end up with the following expression for the kinetic energy. We can then calculate this by using the momentum value we obtained earlier and the values for the electron's rest mass and the speed of light, and we find a value of around 2.4 times 10 to the minus 17 joules. Now, it will prove convenient to express this energy in terms of electron volts, where 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. This is equivalent to the kinetic energy gained by an electron when accelerated through a potential difference of 1 volt. If we convert our energy into electron volts, we find a value of 150 electron volts. And this is the kinetic energy the electron must have such that its de Broglie wavelength is roughly the size of an atom. And so, if we wish to use electrons to resolve atomic size features, you simply need to heat a filament until electrons are liberated from the surface, and then accelerate them through a potential difference of 150 volts, and channel them through a small hole. The emerging electron beam will then have a de Broglie wavelength of around 0.1 nanometers. And this is precisely what happened in 1927 when Davison and Germer fired a beam of electrons towards a nickel crystal and observed a diffraction pattern, confirming de Broglie's matter wave hypothesis. Now, it's interesting to compare the kinetic energy required by an electron to resolve atomic dimensions with the energy of a photon that has the same wavelength. For a photon with wavelength 10 to the minus 10 meters, the energy of the photon can be calculated using the photon energy equation, and we find a value of around 1.99 times 10 to the minus 15 joules, which corresponds to 12,400 electron volts, or 12.4 kiloelectron volts. Compare this with the kinetic energy of an electron with the same wavelength. Photons therefore carry nearly 100 times more energy than electrons need to achieve the same resolving power. As you probably gathered by now, Physics Explained is a channel that embraces mathematics, because after all, mathematics is the language of nature. But I also appreciate that a lot of people love physics, but feel like the mathematics can sometimes get in the way. And I get it, the mathematical side of physics can feel daunting, especially if it's been a while since you last studied mathematics, or you get flashbacks to when you studied in school. Well, the good news is there's an easy way to brush up on your maths, and that's where Brilliant can help. Brilliant is an interactive learning tool that helps strengthen your mathematical skills so you can apply them in physics. If you're just starting out, you can build strong foundations with courses like solving equations, visual algebra, and geometry. They're perfect for developing the kind of mathematical intuition that helps you unpack the ideas we explore in these videos. And if you want to go deeper, Brilliant's calculus and vectors courses are ideal, as they form the framework behind much of modern physics. What I really love about Brilliant is that it makes learning active. You're not just memorising formulas, you're experimenting, reasoning, and discovering things for yourself. It's the same curiosity-driven process that makes physics so rewarding to study. You can start exploring today for free at brilliant.org/physicsexplained, and you'll also get 20% off an annual premium membership, which grants you unlimited access to everything Brilliant has to offer. Just scan the QR code on the screen or click the link in the description. It's one of the best ways I know to make the maths behind physics feel truly intuitive. Now back to the video. Okay, so to summarise, both light and matter can act as waves. For light, we found that if we want to resolve a feature of size delta x, we need photons whose wavelength lambda is roughly equal to that size. and this corresponds to an energy of roughly hc divided by delta x. For electrons, the logic is exactly the same. To resolve a region of size delta x, the electron's de Broglie wavelength must be comparable to that scale, and we saw that this requires momentum roughly equal to h divided by delta x. And once we know the momentum, we can work out the required kinetic energy, which is equal to the total relativistic energy minus the electron's rest mass energy. Now, here's an important point. If we write out the kinetic energy equation in full, then we see that inside the square root there is a term that depends on the electron's momentum and a term that depends on the electron's rest mass energy. Now, when the electron's momentum becomes very large, the product Pc becomes much greater than mc squared. In this case, the mc squared terms in the kinetic energy expression are negligible compared with the momentum term, and so can be neglected. And so we see that in this high momentum limit, the kinetic energy of the electron will be roughly equal to Pc, and we call this the ultra-relativistic regime. So if we now consider electrons moving very fast with high energies and recall the de Broglie momentum wavelength equation, then if we combine this with the kinetic energy equation, we obtain the exact same relation that we had for photons of light. So this is telling us that in the high energy limit, the electron's kinetic energy behaves just like the energy of a photon with the same wavelength. Or to put this another way, once the electron's kinetic energy far exceeds its rest mass energy, its energy scaling becomes the same as light. And so from this point on, since we'll be dealing with very high energies and very short distance scales, we will use the simple relation E is approximately equal to hc divided by delta x, safe in the knowledge that in this regime, we no longer need to distinguish between light and matter probes. Whether we use photons or ultra-relativistic electrons, the same rule applies. The higher the energy, the shorter the wavelength, and the smaller the scale that we can explore. So this now raises a natural question. If increasing energy allows us to see smaller things, can we keep going forever? Can we, for instance, resolve individual protons or even the quarks inside them? And if so, how much energy would that take? Is there an ultimate limit to how finely we can probe nature? Or can we keep zooming in without end? Well, we can now begin to answer these questions using our master equation. For example, if we want to know the energy required to resolve nuclear dimensions of around 10 to the minus 15 meters, we can establish the energy required by plugging the numbers into our master equation. And when we do that, we find an energy of approximately 2 times 10 to the minus 10 joules, which corresponds to 1.25 times 10 to the power of 9 electron volts, which is often written as 1.25 giga electron volts. An energy roughly 1 billion times greater than photons of visible light, and right in the range of modern particle accelerators. And indeed, it was at these very energies that experiments at the Stanford Linear Accelerator Center, SLAC, in California, beginning in 1967, first revealed that the proton has internal structure. By firing electrons with energies of up to around 20 gigaelectronvolts at hydrogen and deuterium, researchers observed that the electrons scattered from point-like constituents inside the proton. These constituent components are known as quarks. And these deep inelastic scattering experiments earned Friedman, Kendall and Taylor the 1990 Nobel Prize in Physics. Okay, so that's pretty impressive. But what if we keep going? What if we increase the energy of our accelerator even more? For example, suppose we tried to probe distances of around 10 to the minus 18 meters, 100 million times smaller than an atom. Well, we can work out the energy required by using our master equation, and we find that the energy required is of order 1 trillion electron volts, also known as 1 tera electron volt or 1 TeV. And believe it or not, physicists have built a machine capable of reaching these energies. The Large Hadron Collider is our most powerful microscope, accelerating protons to around 7 tera electron volts before colliding them head-on at nearly 14 TeV total energy. At this energy scale, it's possible to create ripples in the Higgs field itself and very briefly create Higgs bosons, which exist for a fraction of a second before decaying. Now you must admit that's impressive, but can we go deeper? How far does the rabbit hole really go? Are we limited only by how powerful we can make our particle accelerators, by how much energy we can push particles to, or does nature itself conspire to stop us from looking too deep? To answer that question, let's look again at our master equation. It tells us that to resolve a feature of size delta x, we must use a probe with energy E. Seeing smaller means using higher energy and focusing that energy into an ever smaller region of space. For the scales we've considered so far, that hasn't posed a problem. But at some point, the rules of the game begin to change. Einstein's general theory of relativity teaches us that spacetime isn't a rigid stage. It bends and curves in response to energy and mass. As we focus increasing amounts of energy into smaller and smaller regions, the gravitational effect of that energy becomes significant. The surrounding spacetime starts to warp, pushing further still, and the energy density grows so large that the region would collapse under its own gravity, forming a black hole. And so the logic that once promised ever finer resolution now turns on itself. So when exactly does this happen? According to Einstein's theory, if we take a spherical object of mass m and gradually reduce its radius r while keeping its mass fixed, there comes a point where the density becomes so great that nothing can prevent gravitational collapse and a black hole forms. The critical radius where this happens is called the Schwarzschild radius, and it can be calculated using a remarkably simple equation. R is roughly equal to gm divided by c squared, where m is the mass of the object, g is the gravitational constant, and c is the speed of light, and where we've dropped numerical factors since we're only interested in an order of magnitude estimate. The Schwarzschild radius marks the event horizon, the boundary beyond which nothing, not even light, can escape. Crossing this boundary means crossing the ultimate point of no return. Now, according to Einstein's most famous equation, E equals mc squared, energy and mass can be thought of as equivalent. And if we rearrange for mass, we find m equals E divided by c squared. And if we sub this into the Schwarzschild radius equation and simplify, we end up with the Schwarzschild radius expressed in terms of energy rather than mass. And this is exactly what we needed, because we've already seen that to probe a region of space of size delta x requires energy equal to hc divided by delta x. Now, here is the key point. If we keep making delta x smaller, then the energy concentrated into this region will grow, and there will come a stage where the gravitational effect of that concentrated energy can no longer be ignored. More specifically, when delta x becomes comparable to its own Schwarzschild radius, the energy density becomes so extreme that the region collapses into a black hole. And this is the point where our ability to see smaller fundamentally breaks down, when delta x is roughly equal to the Schwarzschild radius. Beyond this, adding more energy doesn't sharpen our view, it hides what we're trying to see behind the event horizon of a black hole. So let's find out when exactly this happens. To do this, let's first set the Schwarzschild radius equal to delta x, and then if we sub in our master energy resolution equation, we find the following green expression. Then if we simplify and rearrange slightly, we end up with delta x squared is roughly equal to gh divided by c cubed. Finally, if we take the square root, we see that a black hole forms when delta x is roughly equal to the square root of gh divided by c cubed. And this defines a fundamental length scale in nature, one that combines gravity in the form of the gravitational constant g, relativity in the form of the speed of light, and quantum mechanics in terms of Planck's constant. This particular combination of these constants defines what is known as the Planck length, which is often written L subscript p and has a value of around 4 × 10⁻35 meters. Now, you'll often see the Planck length written slightly differently using the reduced Planck's constant h bar equals h divided by 2 pi, which gives the more often stated value of 1.6 × 10⁻35 meters. But the structure of both expressions are exactly the same, and both give values of order 10⁻35 meters. And since we've been working with order of magnitude relations throughout, that distinction isn't important for the conclusions that we will be drawing. Now, it goes without saying, the Planck length is astonishingly small, about 20 orders of magnitude smaller than a proton. At such scales, the very act of trying to see what's happening would cause a black hole to form. And the crazy thing is that if you tried pushing deeper, pouring even more energy into a smaller region of space, rather than resolving smaller distances, you would just make the black hole bigger. In other words, distances smaller than the Planck length cannot be resolved, even in principle. Okay, but can we work out how much energy would be required to get as far as the Planck length in the first place? Well, just as before, we can estimate the energy required by using our master equation. If we set delta x equal to the Planck length and then sub in the expression for the Planck length, we end up with the following equation. And if we then sub in the numbers, this corresponds to an energy of roughly 3 times 10 to the power of 19 gigaelectron volts. That's roughly 15 orders of magnitude higher than the energies reached by the Large Hadron Collider. This totally mind-blowing energy is referred to as the Planck energy. And for fun, let's now ask the following question. How large would a particle accelerator have to be in order to accelerate protons to the Planck energy? Well, if you take the LHC, it accelerates protons around a 27-kilometer ring, with each proton reaching energies of around 7 TeV. So let's imagine simply scaling this up. Then to reach the Planck energy, we would need to increase the energy by a factor of approximately 10 to the power of 15. And so if we scale the LHC's circumference by this same amount, we end up with a circumference of around 4 times 10 to the power of 16 kilometers, which is roughly 4,000 light years. That's hundreds of times larger than our entire solar system, and a few percent of the size of an entire galaxy, an almost unimaginably vast scale. And so we see that the Planck scale is not merely beyond today's technology, it's beyond any conceivable accelerator that resembles the machines we build today. But more importantly, it marks a fundamental boundary in what is operationally meaningful in physics. The analysis we've just carried out tells us that there is no possible way, even in principle, to probe distances shorter than the Planck length. Any attempt to do so would concentrate enough energy to create a black hole, hiding the very region of space we were trying to observe. But the most striking thing is that this same limitation, the impossibility of probing distances smaller than the Planck length, can be uncovered from an entirely different line of reasoning, one that extends one of the foundational cornerstones of quantum mechanics: the Heisenberg uncertainty principle. Imagine that there's an electron located somewhere within a small region of space of size delta x, and we want to observe where it is. And so we shine light into that region and observe the scattered photon. But as we saw earlier, if we use light of wavelength lambda, the best positional accuracy that we can achieve is limited by that wavelength, so delta x is of the same order of magnitude as lambda. And if we want to improve the precision, we must use shorter wavelength light, which means photons with higher momentum, since a photon's momentum is given by h divided by lambda. It then follows that the photon momentum required to probe a region of size delta x is of order h divided by delta x. Now, when such a photon scatters off the electron, it transfers momentum to it, disturbing its motion. And so the uncertainty in the electron's momentum is of the same order as the photon's momentum, which in turn is equal to h divided by delta x. And if we then rearrange this expression, we find that delta x times delta p is roughly equal to h, highlighting the trade-off between how precisely we can localize the electron and how well we can know its momentum. And you may recognize this relation. It's none other than Heisenberg's uncertainty principle. Now, so far, everything here follows directly from ordinary quantum mechanics. But let's now include one additional effect: the influence of gravity. According to Einstein's general theory of relativity, all energy curves spacetime, even the energy carried by a photon, E equals hf. To make this clear, we can work out the mass equivalent of a photon's energy using Einstein's famous relation E equals mc squared. If we rearrange for mass, we can define an effective mass as being equal to the energy divided by the speed of light squared. And if we then sub in the expression for the photon energy, we end up with an effective mass written as hf divided by c squared. Now, here is the key point. As the photon approaches the electron, this effective mass produces a tiny gravitational field pulling on the electron. Now, if the characteristic distance over which the interaction occurs is r, then in simple Newtonian terms, we can estimate the gravitational acceleration of the electron due to this gravitational attraction, and it takes the familiar form, gm divided by r squared. And then if we sub in the expression we have for the effective mass, and simplify, we end up with the result GHF divided by c squared r squared. This is essentially saying that a higher frequency and therefore higher energy photon will pull more on the electron, causing a greater acceleration. Now, roughly speaking, the gravitational interaction lasts for the time it takes light to cross this region, which is simply r divided by c. And we can then actually calculate how much the photon's gravitational pull displaces the electron during this tiny amount of time. We simply use suvat, which you were likely taught in school, in which case we can write the displacement as being roughly equal to at squared. And then if we sub in the expression we derived for a and t, and after simplifying, we find the electron's displacement is given by GHF divided by c to the 4. And so we see that the gravitational influence of the probing photon introduces an additional uncertainty in the electron's position. And we can express this in terms of the photon's momentum by remembering that a photon's energy is equal to its momentum multiplied by the speed of light. And if we sub this into our displacement equation, we find that delta x can be written as gp divided by c cubed. Finally, if you recall, the photon's momentum is of the same order of magnitude as the uncertainty in the electron's momentum, and so we can rewrite the electron displacement in terms of the momentum uncertainty. And there we have it. This represents a new source of gravitationally induced uncertainty. And so we can now combine this with the ordinary run-of-the-mill quantum mechanical uncertainty relation that we love and know so well. And when we do, we end up with a modified version of the uncertainty principle, one that goes by the name of the Generalized uncertainty principle. Now, to get a sense of what this is telling us, let's plot this function and visualize what's going on. Okay, so if we plot delta p on the x-axis and delta x on the y-axis, then we see that the green curve represents the first term and shows how reducing the position uncertainty increases the momentum uncertainty. The red line shows the new gravitational term, whereby increasing the momentum uncertainty increases the positional uncertainty. And then finally the blue line shows the combined effect. And we clearly see that there exists a minimum possible uncertainty. The effect of the new term is to halt the decrease in delta x as delta p increases, and then actually cause it to rise. To find the minimum delta x, we need to find where the gradient of our function is 0. And so if we differentiate the position uncertainty with respect to delta p, we find the following expression, and then we can set this equal to 0. If we then rearrange slightly, we find that at the minimum, delta p squared is equal to hc cubed divided by g. And then taking the square root, we find that delta p is roughly equal to the square root of hc cubed divided by g. The last step is to then sub this expression for delta p back into the generalized uncertainty relation. And if we do this, we find the minimum achievable positional uncertainty. And hopefully, if you've made it this far, you are as amazed as I am, because this is precisely the Planck scale that we encountered earlier. And so, from this entirely different starting point, we arrive at exactly the same conclusion. Nature sets an ultimate limit to how finely space can be resolved. And this result is truly remarkable. From two completely different arguments, one involving black hole collapse, the other rooted in quantum measurement and the generalized uncertainty principle, we reach the same conclusion. There exists a smallest meaningful length in nature, the Planck length. Below this scale, the very concept of distance, and with it the classical notion of space-time, ceases to have operational meaning. So where does that leave us? Well, we appear to have reached an operational boundary. To see smaller, we must use higher energy, but near the Planck scale the attempt backfires. General relativity predicts collapse into a black hole, while the generalized uncertainty principle shows that delta x stops shrinking and starts to grow. It's not that quantum mechanics or relativity are wrong, it's that at Planckian scales, quantum effects and gravity have to be treated together. Any viable theory must put them on equal footing. One such idea is string theory. It suggests that the fundamental building blocks are tiny one-dimensional strings with a finite size, of the same order as the Planck length. That finite size changes the rules. Pushing to higher energy doesn't sharpen your view, it excites more vibrational modes and the effective extent of the string spreads. The string's size therefore builds in a natural limit to resolution. What's remarkable is that string theory starts out as a quantum theory of vibrating strings, but when you zoom out and look at it from afar, the equations of Einstein's general theory of relativity naturally fall out. Gravity isn't added in by hand, it's already there, hidden in the theory itself. And it even contains its own string version of the uncertainty principle, which closely mirrors the generalized uncertainty principle we derived earlier. In both, the first term is the familiar Heisenberg relation, and the second grows with momentum. When they balance, delta x reaches a minimum. In string theory, that minimum is of order the string length, and in the GUP from earlier, it's of order the Planck length. Either way, nature refuses to let us probe beyond that fundamental scale. Loop quantum gravity takes a different route. Instead of introducing extended probes, it quantizes spacetime itself. Its fundamental states are called spin networks, webs of nodes and links that represent quanta of space, with the links corresponding to discrete areas and the nodes to discrete volumes. In this picture, space is built from indivisible chunks roughly the size of the Planck scale, and beneath that, the smooth fabric of spacetime gives way to a granular quantum geometry. Both string theory and loop quantum gravity are active programs of research with real successes, real challenges, and real open questions, and I'll take a deep dive into both theories in the near future. But for now, I'll leave you with the words of Nima Akani Hamed, who says, "Every time we've encountered ideas in physics that cannot even in principle be observed, we have come to see such ideas as approximate notions. However, this instance is particularly disturbing because the notion that emerges as approximate is that of spacetime itself." Thank you for listening, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much, I couldn't do it without you.